Calculus midterm review for Mr. Miller's class. This is for both the AB and the BC class. The test splits on the very last page. These are continuity problems. I want to find the domain of y equals x over x plus 1. Basically, all I do is set the bottom not equal to 0. The bottom is not allowed to equal 0. That's where there'll be an asymptote or discontinuity in the domain. So, in this case, x cannot equal negative 1. So, in interval notation, that's going to look like this. Negative infinity, all the way up to negative 1, union, negative 1 to positive infinity. Number 2, again, the bottom can't equal 0, so I'm going to factor the bottom. That's going to give me x times x equals x squared. 2 times 2 equals 4. Because the difference of two squares, it's going to alternate, plus minus. That means x cannot equal negative 2, and x cannot equal 2. But I have this radical on the top. And that means I'm not allowed to have negative numbers underneath the radical. So I'm going to take what's underneath the radical, x plus 1, and set it greater than or equal to 0. I'm going to solve that, and that's going to give me x has to be greater than or equal to negative 1. Now, in order for me to see physically where this is on the number line, I'm going to graph it so I can see the domain physically. So I have it can't equal negative 2, so I'm going to put open circle at negative 2. I have it can't equal 2, so I'm going to put an open circle at 2. And then I have it can equal negative 1. It's allowed to equal negative 1, so that's going to be a closed circle. But then it says it's greater than or equal to negative 1. So that means I can shade to the right, but not 2. So this gives me this diagram, which shows me precisely what the domain is. In interval notation, this domain is going to read like this. I can have negative 1, and then everything to the right, except for 2. Union, 2, up until infinity, positive infinity. For number 3, kind of the same idea with the radical, but I'm not allowed to have 0 on the bottom. So this kind of goes against what I just said for number 2. Set what's underneath the radical greater than or equal to 0. In this case, plus 2 is greater than 0. Because if I have 0 on the bottom, D and E does not exist. Subtract 2 from both sides, that's going to give me x is greater than negative 2. Now that on the number line is going to look like this. So it's going to be a parenthesis in interval notation, starting at negative 2, going on forever, up into positive infinity. Now I want the asymptotes. Horizontal asymptotes, vertical asymptotes, and or slant or oblique asymptotes. For this, to find the horizontal asymptote, I take the degree of the top and compare it to the degree of the bottom. In this case, they're both 1. So when the degrees are equal, you take the leading coefficient and write it as y equals that leading coefficient divided by that leading coefficient, which is going to give me, in this case, y equals 1. The vertical asymptote for this is going to be where the bottom is not allowed to equal 0. So the bottom is not allowed to equal 0 at x equals negative 1. So there's my horizontal asymptote, there's my vertical asymptote. There is no oblique or slant asymptote in this example. For number 5, notice the degree of the top is less than the degree of the bottom. So that rule for the horizontal asymptote is when the degree is less on the top than on the bottom, you have a horizontal asymptote at y equals 0. Now for vertical asymptotes, it's just like up here, right? Factored that, and I got x plus 2 times x minus 2 on the bottom. So that's going to give me a vertical asymptote at x equals negative 2 and x equals 2. For oblique asymptotes, that happens when the degree of the top is greater than the degree of the bottom. Now because the degree is only 1 greater than the bottom, I can implement synthetic division. So I'm going to put a negative 3 from the bottom into the backwards box, and now I'm going to implement synthetic. 1, 3, 2, those are the coefficients of that polynomial on top. I put a 0 there, some people just drop the 1. 1 plus 0 is 1. Negative 3 times 1 is negative 3. Negative 3 minus 3 is 0. Negative 3 times 0 is 0. But I don't care about my remainder. That has nothing to do with what I'm going to be doing for the oblique. The oblique asymptote is going to be y equals 1x plus 0. Or just y equals x. The vertical asymptote will be located at x equals negative 3. Continuity. I want to find out for what values of a and b that makes this function continuous. So the trick to this is I take the top function and I set it equal to the middle function at the value where they line up, which is at x equals 2. So I'm going to plug this x equals 2 into this top function. And that's going to give me 4a plus, I plug the 2 in for the x, 2 minus b, nothing for that. And I set it equal to this middle. And I plug the 2 in again. So that's 2a plus b. I'm going to do the same process for the bottom two functions. And set it equal to the bottom function, but in this case, where x equals 5. So I'm going to do a plug in for 5. In for x, so that's going to give me 5a plus b equals the next function. I plug the 5 in, that's going to give me 2 times a times 5, that's going to give me equals 10a minus 7. Now, I'm going to simplify these, rearrange it so I have all the a's on one side and all the digits on one side, on the right side. And then I'm going to try to solve this system of equations. So in this case, I'm going to subtract 2a from both sides of the equation. And that's going to give me 4a minus 2a is 2a. Then I'm going to subtract b from both sides of the equation. That's going to give me negative 2b. Now to get this 2 on the other side of the equal sign, I'm going to subtract 2 from both sides of the equation. That's going to give me equals negative 2. The bottom equation, I want to again get all the a's on one side and the b's on the left side and the negative 7 over on it by itself on the right side. So in this case, I'm going to subtract 10a from both sides. 5a minus 10a is negative 5a plus b equals negative 7. Now I'm going to solve this new system of equations over here on the right. I'm going to divide each term by 2. So 2a divided by 2 is just a. Negative 2b divided by 2 is negative b. And negative 2 divided by 2 equals negative 1. Notice I can now solve the systems of equations and have the b term eliminated. Negative 5a plus a is negative 4a. The b's eliminate, equals negative 7 minus 1, negative 8. Divide both sides by negative 4, a equals 2. I take that a equals 2, and I plug it into the simplest equation that I have available. So I'm going to let a equal 2 minus b equals negative 1. Minus 2 from both sides That's going to give me negative b equals negative 3. So for this problem, b is going to equal positive 3. That's where this function is continuous. Equation of a line that passes through these two coordinates, I'm going to find the slope first. So I'm going to do y sub 2 minus y sub 1, which is negative 2, over x sub 2 minus x sub 1, which is 1. So the slope of my line is negative 2. Now in point slope form, I can get two different answers that are equal to one another. This is going to be y minus 3 equals the slope negative 2 times x minus 9. That is a legitimate answer in calculus. They usually don't require me to go any further, such as putting it in point slope form. I'm sorry, slope-intercept form. That is point slope form. The other possible equation would be y minus 5 equals negative 2 the slope times x minus 8. So you have two versions that are equivalent to one another that could show up on a multiple choice questionnaire. First, I'm going to find the slope. So I'm going to stack it, 7, 2. And I'm going to do y2 minus y1, which is negative 2, over x2 minus x1, which is 0. I'm not allowed to divide by 0, so that gives me undefined. Now I use a little memory mnemonic called Vox Hoy to help me realize which equation is which. Notice the u from undefined. That's going to give me a Vox. That means it's going to be a vertical line where the slope is undefined, and it's going to be x equals whatever the x value is from this coordinate. And notice the coordinate is 7 for all of them. So my equation of the line passing through those 2 points is x equals negative 7. Evaluate the limit. Now this is the limit definition of the difference quotient. And when you do the limit definition of the difference quotient, that's the limit definition of the derivative. So basically, all I need to do is find the derivative of what's in that back quantity. And the derivative of that is going to give me 6x minus 2. And that's all I need. First, let's get this taken care of so that we know that these are closed circles. This one's an open circle. That shouldn't even be a circle there. That shouldn't even be a circle there. But that's definitely a closed circle there. An open circle at x equals 3. And all closed circles. And darken this up a little bit. You know how the copiers are. That looks like an open circle. It's actually a closed circle. Okay? So the limit, as this graph as x approaches 1, the y value gets closer and closer to, from both directions, 0. The limit, as x approaches 3, from the left. So I'm getting closer and closer to this 3x value from the left. And that's going to be up here at this value, which is 1, 2, 3, 4, y value there. So that equals 4. The limit, as x approaches 3 from both sides. And this is that pimple popping idea. So I'm getting closer and closer to 3 from both sides. And notice I really can't pop that pimple. They're far away. So that one's a DNE because it's a jump discontinuity. That's a DNE, jump discontinuity. Now, as I approach negative 2, so x approaches negative 2 from both sides, and notice I can pop that pimple right there. That's going to give me a y value of negative 3. Now, these are coordinates. When x is 1, what does y equal? So when x is positive 1, the y value is 0. When x is negative 2, when x is negative 1, 2, when x is negative 2, the y value is negative 3. When x is 0, be careful. When x is 0, it's not this value, it's the coordinate where the closed circle is. So when x is 0, y is 1, 2, 3, positive 3. Now, they want to know the derivative of that graph at x equals 5. At x equals 5, I'm finding the slope at that coordinate. And because that's a cusp, there's no slope there. That's a DNE. You can't differentiate at a cusp, at that sharp edge. Now, what's the slope, or the derivative, at x equals 4? At x equals 4, the slope is that of a horizontal line. So the slope is actually 0 there. Now, what's the derivative at 3? At 3, because that's a jump discontinuity, again, there's no derivative there. It's not differentiable. So that's a DNE is also. One interval from negative 3 all the way from here to 8 all the way over to here. How many discontinuities exist? A discontinuity is where I have to lift my pencil. So I don't have to lift my pencil. I'm still on the page. So to get from this spot to this spot, I have to lift my pencil physically off the graph, off the paper. So there's one discontinuity right there. I keep my pencil on the paper. Now I have to lift it. So there's my second discontinuity. And that's it. All the other parts of this curve, of this graph, are continuous. So there are two discontinuities. One interval from negative 3 to 8. Now notice, it's not including negative 3 or 8. That would be a little tricky at that spot. But on the open interval from negative 3 to 8, how many times is it not differentiable? Well, it's not differentiable at a cusp. So that's 1. It's not differentiable at a jump discontinuity. So that's 2. It is differentiable there because it's smooth. It is not differentiable there because, again, it's another jump discontinuity. So that's the third non-differentiable spot. Before we said that's a cusp, and it's not differentiable at a cusp. So that's number 4. This is another cusp. So that's 5. And the strange spot here, where it has a point of inflection, where the derivative is actually vertical, it's not differentiable there either. So there are 6 spots where it's not differentiable. Limit as x approaches 2 of this. So the first thing I want to do is direct substitution. So 2 to the third power minus 1 over 2 minus 1. That's going to give me 8 minus 1 is 7 over 1. So this limit exists and it approaches 7 as x approaches 2. For number 24, once again, direct substitution. I'm going to plug that in. That's going to give me 1 to the 5th minus the 1 there. Plug the 1 in on the bottom over 1 plus 1. So 1 minus 1 equals 0 over 2. And 0 over 2 is allowed. The limit as x approaches 1 is 0 in this case. This one, if you know the shortcut, all you do is look at the back end and it's that squared. But it's going to be negative 1/3 times 1/3. It's actually going to be negative 1/3 squared, which equals negative 1/9. Some people actually ask how to do this one by hand, so I'm going to go ahead and do it. I'm going to simplify this so it's not 0 over 0. Notice if I put a 0 in there, that gives me 1/3 minus 1/3, which is 0. If I put the 0 in there, that gives me 0 over 0. So that means you can either use L'Hopital's rule, or You can use factoring or simplification. I'm going to use simplification. I'm going to find a common denominator for all these bottoms. And that common denominator is going to be 3x times x plus 3. That's a whopper. But when I multiply that times this top, I'm going to get 3x. When I multiply that times this top, I get negative x times x plus 3. When I multiply it times the bottom, I get 3x squared times x plus 3. Let's tidy this up. This is going to be x squared plus 3x. So that actually I want to distribute a negative, so that's going to be 3x minus x squared minus 3x over 3x cubed. I'm going to leave that as 3x squared times x plus 3 and see what happens. Notice the 3x and the 3x cancel out. And that's going to give me negative x squared over 3x squared times x plus 3. So negative x squared over 3x squared times x plus 3. Notice the x squareds are going to simplify. So this is going to give me, it's a whopper. This is going to give me negative 1 over 3 times x plus 3. And when I let x go to 0, that gives me negative 1/9. It's a little bit nicer if you know the shortcut. For this one, again, I know the shortcut. When I directly solve in 0, I get sine of 0, which is 0, over 6 times 0, which is 0. 0 over 0 means I can implement L'Hopital's rule. So I take the derivative of the top, which is 6 cosine 6x. And the derivative of the bottom is 6. Notice this goes to 1. And when I let x go to 0, that's going to give me cosine of 0. And cosine of 0 is 1. So this is just going to go to 1. More L'Hopital problems. First, you want to do direct substitution. Notice when I substitute the 3 in, that gives me 27 minus 27, 0 on the bottom. And when I substitute the 3 in up here, that gives me an integral, a strange integral, from 3 to 3. And any integral from a number to itself, no matter what it is, whatever that function is going to equal 0 because there's no area under that curve. So I have 0 over 0, I'm going to implement L'Hopital's rule, and I'm going to take the derivative of the top and the derivative of the bottom. And when I do that, it gives me cosine pi times x. You have to remember to plug that x in for t when you take the derivative of it. Over 3. No more dt, it goes away when you take the derivative. All over. The derivative of the bottom is going to give me 3x squared. Now I still continue with the limit as x approaches 3. Now watch what happens. When I plug that 3 into the bottom, that's going to give me 9 times 3, which is 27 on the bottom. And when I plug the 3 into the top, that gives me 3 over 3. It cancels out, and that's cosine pi. And when you unit circle, the cosine of pi is going to be negative 1, 0. So the cosine is the x value. That's going to give me negative 1 at that spot, at pi on the unit circle. So my answer is going to be negative 1 over 27 for number 27. For number 28, it's the same idea. Once again, I'm going to substitute in the 0. When I substitute the 0 in for the bottom, I get 0 on the bottom. When I substitute the 0 in for the limit, as the integral goes from 0 to x, I plug the 0 in there as well, and that gives me a 0 to 0. So the area under this curve is going to be 0. This is going to give me 0 over 0. I'm going to implement L'Hopital's rule. And I'm going to take the derivative of the top and the derivative of the bottom. Now the derivative of the top, I'm going to plug that x into t. That's going to give me ln 1 plus x over x, because I have to plug that x in wherever there's a variable, over the derivative of x, which is going to give me 1. So I don't even need to write the divide by 1 there. Don't forget this limit follows it, so this is going to be the limit as x approaches 0 of this. When I substitute the 0 in, again, I get ln of 1, which is 0, over 0. So I have to implement L'Hopital's rule a second time. The derivative of the bottom is going to give me 1. The derivative of the top is going to give me 1 over 1 plus x. And that limit continues to follow it. When I put the 0 in, this gives me 1 divided by 1, which equals 1 in the long run. Another problem where we're going to try to use L'Hopital's rule. Excuse me. I plug the 0 into the bottom, I get 0 on the bottom. I plug the 0 in the top, I get 2 plus 0, which is 2, and I get an integral from 2 to 2. So the area of this is 0 over 0. I'm going to implement L'Hopital's rule. Now, when I take the derivative of the top, I take the derivative of the bottom. The derivative of the bottom is 1. When I take the derivative of the top, I have to plug in 2 plus x. So this is going to give me the sine of 2 plus x over 3x, 3 times 2 plus x, which is the same as x plus 2, plus 2, all over 1. Don't forget this limit, as x approaches 0, follows it. Now, when I let x go to 0, this is going to give me sine of 2 all over 3 times 2, which is 6, plus 2, which is 8. And I think that's my answer.